From our own experience all the way back to our childhood, we know that different states of matter have different energies. So changing states of matter relates to a change in energy. Ice is cold, and when you touch it, you can't touch that for too long until your skin is also very cold. And steam is extremely hot, and that would burn you very quickly, much more quickly than many other hot objects because of the way the energy is transferred in each of those cases. So as we change between our phases, we know that we're going to be gaining or losing energy as well. Some changes of state are endothermic because we have to put energy in order to make that happen. The endothermic changes would be melting, vaporizing, and one that we're maybe less experienced with, there we go, is sublimation, going straight from solid to gas. So with those, they will not always feel cold, but energy is always coming in. If I'm trying to get water to boil, that has to happen at 100 degrees. So we cannot just say, oh, the fact that it's on the stove means that it's exothermic. We need to think about the flow of heat. The opposite of each of those is exothermic: condensation, deposition, and freezing. We are removing heat from them. Ice feels very cold, but it is exothermic in terms of the process of freezing because we are taking heat out of the liquid water to turn it into the solid state. During the actual process of change, the system is not changing in temperature. Ice freezes because the surroundings are colder than it, and energy is going out to those surroundings, yes. But the spacing of the particles, the freedom of motion of particles, the potential energy of those particles is what is changing during that process. So heat is flowing in or out because there's a difference in temperature of the system and surroundings, but we aren't changing temperature. So when we are looking at those changes in state, it takes a certain amount of energy to make that happen. Right here are some common values for water. Water's the most common substance that we'll look at in terms of changes of state and changes of temperature, because it's very often used as either a system, a surroundings, and occasionally both in terms of thermodynamics experiments. But we have a different temperature, or excuse me, not a different temperature, a different amount of heat to undergo each of those. So when we are doing the vaporization change, we would call that the delta H, which is either the heat or the enthalpy of vaporization. It's almost 2,300 joules per gram. That's when we're talking about H2O, and that much energy needs to be gained in order to boil or lost when condensing, The heat of fusion, or enthalpy of fusion, is related to the solid to liquid transition, which is 334. When melting, we put that in. That's how much is removed when we freeze. And then sublimation is actually a combination of these with other energy accounted for, but it is energy in or energy out as well. So the quantity is the same, just the positive and negative value is different. And you'll see different values reported from different textbooks, from different websites, but they're all very close to these values here, and you would be given the values if you need to use them. But one thing that we can understand is, as we tie this to graphs or other descriptions of this, we'll see that we have very big differences there. When I am melting, if I come back up here, I am going from particles that are held in place but fairly close together to liquid molecules that are free to move but still very close together. I am breaking some of the attractions and increasing the potential energy sum, but I have much less increase compared to the boiling process, where I have particles that are still very close to one another to particles that are super far apart. So the magnitude of these is a very good indication of how much energy or how different the states are from one another. And we can also, and very often, connect these to a heating curve or to a graph, which shows how changes in energy are related to changes in temperature. Right here, this one shows as time, because we can just think about adding heat for a certain constant amount of time to see what happens to the temperature. We would most often see these for a pure substance. There are a few mixtures you could see this for, but for the most case, we would look at one substance, either an element or a compound at a time. And we could think about the lowest energy, lowest temperature part of the graph being the solid, the highest energy, highest temperature part being the gas, the middle part being the liquid, and then accounting for the changes in state or changes in phase in between. So we've got our axes labeled, and it's important to note that we have horizontal portions that show a change in energy without increasing the temperature, and we have sloped portions, which are places where we are changing the temperature as we add heat. So the Y value for those horizontal portions is important. If we're looking at the heating curve of water, they would happen at 0 or 100, or any other substance, they would happen at the melting and the boiling point. And that horizontal length corresponds to how much energy is associated with those changes. So this graph, it probably isn't the graph for water because we see two sections very close to one another in length of time or energy. The sloped portions are related to that linear relationship or that connection between heat and temperature, or heat capacity, or very often specific heat, because throughout this whole process, we're dealing with just a single sample, so the mass is staying constant. The slope is based on how much heat is needed to do that. A steep slope, and I have a very steep slope on this graph, is showing I have a big change in temperature for a very small change in heat. That corresponds to a lower specific heat. So we need to be careful to recognize that the slope itself is not the specific heat value, but it is connected to it, because specific heat is joules over Celsius, and here our change in Y is Celsius, and the change in X is very often our heat or our joules. So they're really inverses of one another, although they are tied. A very steep is a very low specific heat. So as we're looking at this, we can look individually at just a single change in state, or we can continue to add heat and see after we've changed our state by increasing or decreasing our potential energy, we can then increase or decrease the temperature or the speed of the particles until they're moving so fast in the case of heating it up, or so slow in the case of cooling it down, that they then are ready to undergo the phase change at the boiling point for the higher, there we go, horizontal line, or the freezing point for the lower horizontal line.